Varun Mohan is a CS graduate currently pursuing M.Tech ECE Embedded System at National Institute of Electronic and Information Technology. He is interested in RTL design and building systems and accelerator with FPGAs. He is also very keen about bare metal C programming, hardware, software, co-design, and computer architecture. For this, I'd like to invite Varun to start his presentation. Varun, go ahead, please.
Thank you, sir. Let me share the screen. One second, sir.
Okay, it's okay. Please take time.
So is the screen visible?
Yes, Varun, go ahead.
Hello?
Yes.
Okay. Okay, sir. Before I start, I would like to thank Ganeshan sir and Open FPGA, Open Power Foundation and IIT for giving me this opportunity to speak. So this is about me. As I already told, I'm a CS graduate. Currently, I'm doing my master's in embedded system from Litex, Calicut, and I'm interested in RTL and FPGA-based design. Also like the Abraham C programming and computer architecture. So this is the agenda for today. So it's going to be a brief presentation with a demo. So we're going to basically talk about an open source flow to for logic synthesis. So we'll cover how to do function verification of your RTL code, then how to synthesize and map it to a standard library, and after synthesis, how to do gate level simulation. And I'm also going to show you how you can use the same flow to target a cheap FPGA that you can buy off the shelf. In the end, we're also going to talk about Litex, which is a framework for generating SOCs, and I'll also show you how you can simulate an SOC which uses microwatt as the CPU. So the first step in front-end digital design is like after you have your code is verifying it. So first step is simulation. So simulation basically you have the design. You want to make sure that it is working as per specifications. So basically you have your input, which is your design as well as the test bench, and you feed it to the simulator. You observe the output waveforms and check whether it is performing as per the requirements. So the tool we're going to be using here is iVerilog. So this is a basic flow which you can use for in iVerilog. So you have the design as well as test bench. You pass it to iVerilog. iVerilog will create an executable. You execute the executable and it will create this VC file, which is called the value change dump file. You pass it to GTK wave and it will give you the time diagram. So all these I'll show a demo after the presentation. So next step is once you have verified that your design is functionally correct, next step to go about is logic synthesis. So the basic idea is you have your code which is written in some behavior construct. Like in this case, this is a mux written in Verilog. Ultimately, you want basically a collection, a set of gates or flop interconnected set of gates and flops. So this is the basic idea of synthesis. You can see here on the left side you have the Verilog code. On the right side, you have that synthesized netlist. Synthesis can be further divided into 3 steps broadly. First one is translation. So here, the high-level behavior code is converted to its corresponding logical gates or flops. So these two are different. If you can see here, this is generic mux. This is the mux actually mapped to an standard cell library cell. So that we will see later. So once then the logic synthesis tool also does a lot of logic optimizations. Like in this case, this is called constant propagation. Since this is always 0, it can be easily converted to an NOT gate. So the synthesis tool does a lot of optimization techniques like this. And the last step in synthesis is mapping. So once you have the synthesized netlist, like in this case, the Verilog code synthesizer had detected that it needs a mux, and based on the backend that you are targeting, like an ASIC or FPGA, each individual component has to be mapped. So in this case, we are going to target some called the Skywater open source PDK, which is available open source online, and we are going to use the standard cell library from Skywater PDK. So once you do the mapping with uses using the Skywater PDK Liberty file, the mux gets mapped to the corresponding standard cell from the Skywater PDK. So you can see here on the left side, this is a plain mux, which is generic mux, and it has been mapped to a standard cell from the Skywater standard cell library. So after synthesis, what next? So synthesis is actually a very complex algorithm. It is basically a complex algorithm running on your design, so it can go wrong. That is one thing. Second thing is there are many coding practices that can result in in synthesis tool, like generating logic that is not intended. Like some of the common cases are like missing signals in the sensitivity list, using blocking and non-blocking statements, like well, in like where they're not supposed to be, and a missing statement in case blocks, which is like a frequent reason for inference of latches. So gate-level simulation is simulation after on your the synthesized netlist. So basically the flow is similar, like if you are using iVerilog, it is similar. You have the good thing about this is after gate-level simulation, in the synthesized netlist, the inputs and outputs are the same, so you can use the same test bench. Only different is that instead of using your original VHDL code, you're going to use the synthesized netlist. Apart from that, since the content of the synthesized Verilog is now the mappings for the standard cell library, you have to give the Verilog models for each of the cell library as input to Verilog as well. So this is the same flow. You have the test bench, which can be the same as your functional verification test bench. This is the synthesized netlist, which is obtained after logic synthesis. Then you have the standard library Verilog models. Test is the same. You pass it to Verilog, it will create an executable, and you can execute that, which will create the validity change dump file, which you can view using GTK. So I'll quickly show a demo of this. So we're going to synthesize basically this code, which is a basic code for it to cross on mux. So the synthesis open source. First, we can do the functional simulation. For that, I'm going to invoke iverilog. To iverilog, you can pass the original your design verilog file as well as the TB touch bench. So this is going to create a executable a.out in your current working directory. So you can run that. It created this mux.vcd. The value change done, you can open with gpk wave. And you can add the signals to the window. And verify this. So we can see that when S is 0, I think it is following B, output is following B, and when it is 1, it is following A. So appears that our mux is working fine. So next step is using, we have to synthesize this. So the tool which we are going to use is called EOSys. The first thing is we have to load the standard cell library from the Sky130 PDK. So this is how you do it. Read liberty minus lib Sky. Next, you can read your Verilog source file. So mux.b. And so you can use the synth minus top and your top module name to synthesize that. You can see that it has synthesized, it has inferred a mux. You can use the command show to see this. Currently, you can see that this is kind of a generic diagram, like it is showing that it needs a mux. So next thing is we have to map, do the mapping, like you have to map this mux to the standard cell library cells. For that, you can invoke ABC, that's liberty. Now if you execute show, we can see that rendering mux has been replaced by the mux from the Sky130 standard cell library. You can write the output of output Verilog file using write Verilog. Okay. So we have finished synthesis. Next step is we can do the gate level simulation to ensure that there are no simulation synthesis mismatch, and in fact the synthesis has done the correct job in inferring the logic which we indent. For that we can use iverilog itself. The first file with TB will be the same as I said, because even after synthesis, the primary input and output of our design does not change. But instead of using mux.v, this time we are going to use mux synth.v as the one of the sources. Next, we also, as I already told, we have to also include the Verilog models for the standard cell library cells. So those are in Sky. again execute. It was generated an executable. You can execute that. Next.vcd was again created. So you can view with GTK wave. So this is when it is following B, otherwise it's following A. So even after synthesis, it has inferred the correct logic. So any doubt in this part? Next, I'm going to move to a demo where I can use the same flow to generate bit stream for an FPGA. Hello.
Yeah, looks good, Varun. Go ahead, please. If there is any question, participants, please post it in a chat window or a question and answer window.
Okay, fine. Next, we are going to use the same kind of flow to target bit stream generation for an FPGA that you can buy off the shelf. So we're going to right with me. I have the Lattice ICE 41K with me. So this tool set.
So do you have physically the FPGA at your home, Varun?
Yeah, I have it. Yes, sir.
Maybe you can show that actually, so that there are people from many colleges interested to learn all this.
Yeah, sure, sir. I'll show it. I will first load the bit stream and then show.
Sure. Yeah, this is a perfect example, team. Many people can get an advantage of the LibreSoc kind of program also can be programmed using the FPGA. So let's see. Thank you.
Yes. So what I have here is a basic code. Like I have a development board which houses a basic FPGA, and on that board I have 5 LEDs. This model is LED 1 to 5. So and on there is a 12 megahertz clock as well. So just to make the demo a little bit visual, what I have done is I create a 26-bit counter, and this counter is incrementing on every clock tick, and I have attached the most significant 5 bits to the LEDs. So basically, you will see the LEDs toggling at some rate which is visible to the human. So I'm not going to explain the code here. This is basic Verilog, and another thing is this thing. So Yosis, the commands which I showed earlier using Yosis, you can write it in a single file and pass it to Yosis. So it can read it line by line, executes it. That is what I have done here. So this is the same thing. Read Verilog. You read the Verilog file, and synth ICE40 must stop blinking. So here, thing is, instead of just using synth, we use the command synth ICE40. Which is specifically targeting the ICE40 FPGAs. And again, our top module is Blingy. So you say top Blingy. And you can write the output synthesis netlist in multiple formats with Yosis. So here we are writing it one in JSON form, which is used by our placement and routing tool. And second, I write it in pure Verilog form, which can be used for post simulation as well. So the under steps have been documented in this make file. So first step is you execute that .ys file with Yosis. It basically synthesizes your Verilog file targeting the ICE40. And after that, since this is an FPGA, you have to do the place and route, which is done by this tool called Next PNR ICE40. and one of the input is the blinky.json file which was created here. And another file is this PCF file, which is like the constraint file. If you're familiar with FPGA programming, the IO constraint. So basically, it is saying like these are pins on the FPGA, physical pins 19 and 98, and we are assigning them to these names which we used in the module, like clock one, clock LED1, LED2, etc. So this is going to generate the bit stream in an ASCII format, which is again converted to binary format using this tool called IcePack. And IceProg is used to program the FPGA using the binary file. So the under this host of tools is under a project called Project IceStore. So you can check it out. All this IceTime, NextPiano, IcePack, IceProg, etc. So in this case, to generate this stream, I just have to run make. So it is going to execute all the commands one by one, and finally it is going to create that blinky.bin file. And next I can use make prog to program the binary bitstream to the FPGA, and I'll show the FPGA now, like what it's doing. One sec, cam. I'm not sure if you can see it. The LEDs are a bit bright, but I think you get the idea. The LEDs are like blinking like in that specific pattern.
Yeah, very good. Yeah, it's highly visible.
So this is that FPGA development board. It is called the Lattice iStick. You can buy it off the shelf.
How much it
It's
costs?
also say basic FPGA. So if I remember correctly, it's around 3,000 something.
Wow.
I'm not sure about the import it is. I don't remember. I bought it like quite some time ago.
Yeah, locally in India, right?
No, it is imported.
If I may, we actually use the exact same tool chain in LibreSoc, and so you can get the Lattice ECP5 boards for we're using that are the ULX3S is around $70 US. The more advanced version with the 85K lookup tables is 130, and you can also get the Digilent Artix A7100 for about $200 US. So, which is perfectly capable of running Microwatt and LibreSoc. You're looking at about 20,000 LUT4s for both Microsoft and LibreSoc in the integer configuration. So. Yeah, you don't need several $1,000 zinc boards, for example, for this. You don't need 300K.
Yeah, this is cool. Yeah, this is cool. I think we can take this as a prototype, and communicate to all the universities who are participating as part of Open Power to buy this and try it out. All these options, LibreSoc and the Microwatt and all the stuff. Sure. Thank you, Luke, for addressing this.
Okay.
And thank you, Varun. And yeah, this is good. Any more things?
Yeah, I have more slides. Yeah, I just cover with Litex.
Yeah. Go ahead, please.
Okay, so next we are going to see a framework called Litex. So I'm also a beginner, so this is like a quick getting started guide for you. Like you can how to get the thing installed and start playing, so you can tinker around and get a feel of how it is happening. So it is basically a framework for creating basically SOCs, and it is based on MyGen, which I think was discussed in one of the talks, and it supports buses like Wishbone and AXI, and you can integrate your existing VHDL Verilog system Verilog code in Litex. And the most exciting part now is that it supports multiple software CPUs, including microwatt. So if people who are not aware of microwatt, it's an open source processor core implementing the Power ISA 3.0 instruction set. It's completely open, written in VHDL. I think it's all written in Chisel as well, but yeah, it is completely open source, available in on GitHub. So this is a typical design flow on with Litex. This I have copied it from the latest documentation. So you have the latest framework, and you have the latest core ecosystem as well. There are so many cores that you can use. Like you can pull it in, like there is Ethernet, PCIe, etc. And you have the FPGA tool chain, and this uses Python as it is like programming in Python. So if you want to get into this, I think you will have to be like good knowledge of Python is required, especially the OOPS concepts. I'll just show you a quick demo of this. Under the SOC, sorry, YOSIS building process, sorry, synthesis has been completely documented here. I will share the a link in the chat box. You can see from start to finish, everything is documented. So you go through this GitHub link. And okay, so this is complete documentation of how you can get Litex installed on your Linux system. So the installation, it was there are so many dependencies and you have to install so many things. So we had completely documented this. You can follow this from start to end, and you will have the Litex framework installed. Each and every step, this has been verified as well, so it works. Maybe only thing is that some dependencies might be missing, because I am already using Linux, so I might have already installed some dependencies. So in this case, you can inform me, or you can create a pull request to this, so I can add it to the documentation. So you can follow this to get Litex installed on your system. Then once you have that, you can clone this repo, and let's open the space bar. So if you clone this, you'll get something like this. So first thing you can try is you can actually run the simulation for an SOC running the microwatt CPU. For that, you just run this command, run sim.sh. Please follow all the steps mentioned in that GitHub repo one by one, because there are a lot of dependencies. Like this also requires the PowerPC cross compiler, because and stuff like that. So everything has been documented, so you can simply follow that. Meanwhile, it is running. I will show you one more thing. Because there are quite a few tutorials from the creators of Litex itself, which they take you from the from basics, like from FPGAs till.
Yeah, my name's Alan Cantor, and I'm going to talk about decoupling from.
Sorry,
Hello.
I think somebody played something. Sorry,
Okay.
Go ahead.
Yeah. So I'll share that link also. So in this, there is a lab called Microwatt. Sorry, Lab 004, which I have modified a bit so that it can generate bit stream of the SOC with Microwatt as the CPU. So I'm not going to run the build process here because it is going to take some time, but it is already built. And if you go inside the build directory, there are two subdirectories. You have the software and the gateway. Inside the gateway, you will see the Vivado related stuff. Here I'm using Vivado. I think it can be done with SymbiFlow as well, but I was not able to get it running in time for the presentation. So I'll update it in the GitHub repo if I'm able to do it. And you have the generated bit stream, which you can program your FPGA board with. So once you have programmed the FPGA, now you have the SOC, like your FPGA is running as a SOC. Next thing is actually loading some firmware onto the SOC, which is so for that, if you can see, this is the software folder, which contains all the generated basically C headers and other drivers for the cores that you instantiated or used in the SOC. So if you are familiar with a microcontroller or some similar programming, it is like the peripherals are fixed and you have the like sensors from ARM or the HAL library from the vendor, which are used to interface with the device register, basically memory mapped devices. So here in this case, you are building the SOC by yourself. So the tool itself generates all those what do you call the headers and the C driver files for you. So you can include those as includes in your project and use those to access the memory map registers of your of the peripherals. So you can see this is a sample firmware which has been written. So if you see the make file, you can see that it is pulling it from that that software build software directory. So all those the startup script, etc. I think you get the point. This is the basic structure of a project using Litex. So you will have the build directory, which will contain the generated bit stream as well as the auto-generated header files and driver C programs. Then you can write your own firmware, and you can include all those, pull in those header files, and access those peripherals. Let's see what's happening here. Yeah. So this simulation has run. You can see here it is the CPU is microwatt at 1 megahertz something. And yeah, you can play around, type something. I don't know if this supports loading another here, whether you can load another, firmware. Yet to try that. Okay, so that's it from my side, sir.
Yeah, Varun, it's a great opportunity for people to listen to your demo as well as your FPGA and your the enthusiasm on having everything at home and doing a lot of things. Anyway, I look forward to work with you more on LibreSoc and the microwatt and Litex and many more things from IBM and OpenPower and also our partners. And this is going to be a kind of a collaborative effort. And also probably I may want you to educate many students who are interested to learn about it also. Maybe hundreds of students want to learn all this. Maybe we can run a another session with a kind of a real-time demo or something. I mean real-time hands-on or something like that. That would be a great opportunity for people. Okay, any questions, audience?
Sure, sir. I'm also looking forward to.
Yeah, thank you, Varun. Thank you for a wonderful effort, and I really appreciate it. In a very short time, you created the demo and everything. I really appreciate it. Thank you. And any questions? Any questions from audience? So if there are any questions, please post it in the chat window or a question and answer window. In interest of timing, I'll have 15 minutes.
There was one, somebody would like to know where the source code for the demo and the documentation is available online.
Yeah, he's going to be posting that. He shared with a lot of people.
Brilliant.
I
Varun,
will just
share
post it.
the
Just post it.
GitHub. Yeah, sure.
Thank you.
Yeah, I'm doing it right now.
Yeah, thank you, Varun. Thank you, Luke, for addressing that. So